If an electromagnetic wave is travelling through anything other than a vacuum, some of the wave will be absorbed. The reason includes some spoilers for modern physics that you're going to be doing next term, but let's have a preview. Light is absorbed because atoms have electrons in shells, and rather than actually staying in the lowest shell closest to the nucleus, electrons, when they have a bit of energy, can actually jump between shells as long as there is a vacant space in a further up shell that they have enough energy to reach. Because each shell has a particular energy, and the further out shells have higher energy than the ones nearer the nucleus. So an electron in the simplified atom in the diagram you can see would need a packet of energy to jump from the inner shell 1 that has energy E1 to the outer shell that has energy E2. Then, if it jumps from level 2 down to level 1, it has to lose a packet of energy. Those packets of energy are shown as the wiggly lines in the diagram, and they represent photons of light. I'm using the term light loosely here. It really could be any electromagnetic wave. Now, the energy of a photon actually depends on its frequency. Again, you'll look at this more in modern physics, but it makes sense. We know that the high frequency end of the electromagnetic spectrum is the dangerous end, and that X-rays and gamma rays have enough energy not just to make electrons jump between the shells, but actually to knock them out of orbit altogether and ionize that atom. So it takes one particular frequency of light to provide the exact energy to make the electron jump from level 1 to level 2. And that same frequency of light that has the exact same energy will be emitted when the electron jumps from level 2 to level 1. Now, atoms of different elements have different spacings of the shells and different particular energies of the different shells. So the frequencies that an atom of a particular element can absorb or emit are limited to very specific values. And each element can actually be identified by the specific frequencies that it will absorb or emit. And we can see here an example from astronomy. Now, let's imagine we have a hot source, that red dot on the left, and let's say that's a star. If we look directly at the spectrum of electromagnetic waves coming from that star, if it's something like our sun, it will have a peak in the middle of the visible spectrum, and its light will show up as a continuous spectrum. Now, let's imagine we have a bunch of gas that is quite hot. That's at the top there. Now, that gas will have enough thermal energy that electrons are actually jumping between energy levels. And each time an electron jumps down a level, as you can see inside the hot gas there, it will give out a photon. So it will give out light of a very particular wavelength. So you can see there on the right what we call an emission spectrum that has only very specific lines of colour being given out, and each line corresponds to a particular jump between energy levels. In fact, the bluer lines correspond to bigger energy jumps, maybe from level 5 or 6 down to level 1 or 2, whereas the red lines are smaller energy jumps, maybe from level 2 to 1. Now, at the bottom, you can see if we have the same gas, but it's a cool gas, and imagine it is between us and a star. So this is something that happens when astronomers look at nebulae that are clouds of gas. Now, this cool gas will be absorbing some of the light from the source that is on the other side of it. And so the light will be absorbed, and it corresponds to exactly the same wavelengths as the light that is being emitted when the gas is hot. And so a hot gas gives out what we call an emission spectrum that is black with only a few lines of light. But the cool gas gives what we call an absorption spectrum because it needs a hot source giving out the entire rainbow, and the gas is actually subtracting very specific frequencies that can be absorbed as the electrons jump between levels. Now here's a question for you. We've just seen that an atom can absorb a photon and jump up an energy level, or it can jump down an energy level and emit a photon. So the picture at the bottom shows the visible spectrum that we see from the sun. And it has black lines in it. These are called Fraunhofer lines after the man who first observed them in 1814. I'd like you to have a go at answering now. What kind of spectrum would we call this, of the two kinds that we've just seen? And what elements do you think, or where are the elements that are causing these lines?